Hello, today we'll be looking at Gvisor CTF Writeup for Google CTF 2023 from SANDBOX category. In this challenge, we are given a Gvisor RNSC binary that executes an arbitrary program in SANDBOX. The Gvisor binary contains a new syscall 666 to read the flag. However, it is only added to the ARM64 sys table. We cannot use ARM64 syscall because we run the AMD 64 version. So, how do we invoke the getFlag syscall? The gvisor challenge also has some bugs introduced, namely both functions restore FPS and save FPS do a copy and an unsafe slice with the offset FPS that is provided by the application via shared memory, the sysmsc, hence untrusted. The results an outer bound of read and write and can allow an attacker to compromise the sentry process. In our case, the memory corruption vulnerability provides us a way to invoke the getFlag syscall. Intended solution. As hinted in the challenge, there is a getFlag syscall which is of interest. In order to execute it, we have to corrupt the syscall table and, for instance, replace a function pointer of the syscall with the address of the getFlag. After that, the flag can be retrieved with syscall sys underscore any number uh, flag. To achieve that, we need to turn our out-of-bound read parameters into arbitrary r/w parameters, which can be easily achieved by finding out the base address. For that, the challenge already provides a free information leak, namely this is message struct containing the following sentry address. The that holds the pointer to the sysmessage struct in the sentry address space. Since Gvisor is not compiled with PIE, platform independent something, its base address is always at 0x004000. Okay. Therefore, ASLR doesn't need to be defeated. So finally, we need to figure out how to trigger the out of bounds read and write or vulnerabilities. Looking at the code, we can find many instances where save FPS is invoked through full state. For instance, when a child process is traced, the FP state is saved in the struct. The type state struct regs registers FP state FPU dot state colon wait, which can be fetched for example at func state ptrace get regset regset u in pointer tst function parameters switch regset different cases different defaults to zero. So all it takes to leak the out of bounds data is to trace the child and make the child process trigger a signal with a malicious FP state as in S message. Okay. After changing the signal in the process, we can simply call ptrace ptrace get regset PID and IOV to fetch the data. Since this is called stubs sets the FP state to a constant address, we use a separate thread and perform a race condition to change the value race to set to malicious FP state. Based on the content of the leak, we can deduce whether the race uh, was successful or not. If not, then we repeat the leak. We use the primitive to leak the syscall table max 080 bytes. Our strategy is to modify the content of the syscall table, redirect the pointer, and then write back the syscall table. Looking at the code, we can see that a restored FP state is invoked in switch to app, which switching back to the application after the signal. Also, we can see that the signal restore the content of the c.fp state is overwritten with the content provided by the application, which is fully controlled. fp state and then we install a signal handler, example signal sig to sig handler, and in that sig handler we modify the fp registers like memcopy ucontext.fp arbitrary content 0x80 with the same race thread on a sig return. We overwrite memory content with an offset provided by the application. Again with the offset to the sys call table. After the signal returns, we can invoke syscall sys_enum with the flag, and if it returns 0x1237, then the syscall function pointer has been redirected to successful and the flag buffer contains the flag, otherwise repeat the process. Thank you.